Right, our next set of objectives here is to start understanding what it means to have things connected in series and for circuit elements to be connected in parallel. Now before we begin this here, I just want to emphasize that a lot of these things here in the first week or two are really to just give us the basic tools. The latter half of this course will start looking at some applications and examples where we can see circuits that will actually, quote, do something. Right now we're just learning the basic tools to be able to analyze those circuits. So let's first start off here. Again, this is really, we're not going to be talking about circuit analysis at this point. What we're going to really focus on in this video is being able to understand the difference between series and parallel connection. Now, a series connection, well, actually, before we write this down, let's just look at a device here. The devices we've looked at so far are what we would refer as two-terminal devices. And so when we say two-terminal devices here, the idea is that, well, we have a terminal here. We call this, terminal 1. I mean, you don't have to call that terminal 1. I just do. And then this one would be, of course, terminal 2. So we got a two-terminal device. And that's what we have, because we see that, well, for instance, a resistor is clearly a two-terminal device. Our voltage supplies are two-terminal devices. A current supply is a terminal device. And really the only other thing we've talked about is some kind of dependent power supply. Now, we know that a dependent power supply could be both current or voltage. I'm just going to leave it as a triangle here. And it's got some K times, it's either a voltage or a current. In this case, I'll just say it's a voltage. But that's still a two-terminal device. So we're going to want to know if these are connected in series or in parallel. We're going to be able to get a lot of useful information being able to just determine whether things are in series or parallel. So let's go ahead and now talk about series here. Both of them I don't think are difficult to do, but for some people it takes a while to be able to just look at a circuit and recognize whether they're in series and parallel. And that was the case for me. It took me a couple of days before I really understood series and parallel and was able to suddenly I get it, series and parallel. So that's what we'll focus on here as far as being able to determine series from parallel. So a series, components connected in series, have one and only one terminal in common. And this is for, to emphasize, this is for two components. So let's look at an example here. A simple circuit. We'll have 3 resistors. I'm not putting any values down because we're not doing any circuit analysis, and a voltage source. What we want to be able to see here is that these devices, these circuit elements, are connected in series. Now when we say that they're connected in series, really what we mean is that, well, this voltage source is in series with R1, then R1 is in series with R2, then R2 is in series with R3, and R3 is in series with the voltage source. But instead of saying all of those things, we just say that the circuit elements are all connected in series. So even though our definition is dealing with just two components, when we have more than that, we say, oh, okay, well, but they're all connected in series. And we can see that just by looking here. If I look, basically you're looking at a node. Well, we can see that R1 and the voltage source are connected in series because they share this terminal in common. But then if I look at their other terminals, whoops, it's not what I want here. Hit the wrong thing. If I look at the other terminals here, if I look at this terminal and this terminal, these two terminals are not connected directly. Now, I'm going to just do a dotted line here. I mean, this will be silly, but if I put a wire here, actually I'll draw it in, then those terminals, those devices would no longer be in series, and of course the circuit would be completely different. So let me erase those here. And we can do a similar thing to see that, well, R1 is in parallel, not parallel, R1 is in series with R2, because again, if I look at R1 and R2, they share this terminal that I'm just making bigger and bigger in common. But then the other terminals that these devices have, this terminal here and this terminal here, are not connected together. So that's why R1 is in series with R2. And then I'm going to, stop playing this game here of, showing every single one, because we can clearly see then that all of these components are in series with each other. All right. But let's talk about, before we move on with parallel, let's talk about something that's critical with series circuits here. Go away, auto rotate. That if I'm going to draw here a loop here, but we're going to draw this as a current here. So I'm going to draw some current I here. And for a series circuit, the current through all components is the same. So that means the current going through R1 is the same as the current going through R2, which is the same as the current going through R3, which is also the same as the current coming out of this voltage supply. So that's why I just labeled it as I. There's no need to say IR1 or IR2 or IR3 because they're all equal to each other. And I'll just emphasize that maybe here that I is equal to IR1, which is equal to IR2, which is equal to IR3. Now, one thing here is that typically the voltage drop across the components will be different. So don't think that the voltage is going to be the same across these circuit elements. The current will be the same, but the voltage will typically be different. Now, the reason I say typically is there is a way to make the voltage drop across R1, R2, and R3 the same. It won't be the same as the voltage supply, but I can make R1 and R2 and R3 the same voltage drop. And some of you might be thinking in this video, well, you might see how you could possibly do that, even though we really haven't talked much about the series circuit like this yet. But kind of an obvious answer to me would be like, oh, well, you just make all of the resistors the same value. So that would be a way you could get the voltage drop across the resistors to be the same. But that's why we say typically they're different, because even if you set these all as 1 k ohm, in theory, yes, the voltage drop would be the same, but in practice, 1 k ohm resistors are going to have a tolerance, and so the voltage might be different. All right, so let's move on to parallel. So parallel circuits, two components are in parallel if both of their terminals are connected together. So in this case, we're not talking about having only one terminal, we're having both of the terminals connected together. So let's look at an example here of a parallel circuit. And again, we'll have a voltage supply, R1, R2, and then R3. Now these are all connected in parallel. And again, we only examine two devices at a time, but let's just go ahead and pick two devices here. Now it turns out that it doesn't matter which two devices you pick, but I'll just go ahead and pick R1 and R2 to examine. So we're going to see, are these devices in parallel? And then we can clearly see that, well, we have a node up here that's connecting, if we call this the top terminal, terminal 1. So this node here is connecting terminal 1 of those two resistors together. And then we can see this node at the bottom here is connecting terminal 2 of those two resistors together. So R1 is in parallel with R2. And of course, because this node is connecting, this top node is connecting all of the terminal 1s of all the components together, and this node here is connecting all of terminal 2 components together, that all of these components are then connected in parallel. So these are all in parallel. Now there are some things that are important here for this to recognize as well. For parallel circuits, the voltage drop across each component is the same. So what that means here, if I draw on this picture, I'm going to erase these little boxes that I made, is that if I look here and say, well, there's this voltage, and I'll just call it V1, and then there's a voltage V2, and then there's a voltage here V3. So we've got these voltage drops across resistor 1, 2, and 3. What this is saying is that our voltage supply, whatever that is, that's the same thing as V1, which is equal to V2, which is equal to V3. Now, the current through each component is usually different. And just like in the series circuit, we can come up with a scenario where the current through each of the three resistors is the same. And I think that's easy to kind of think about how you would do that. Remember, resistors, the name means that they resist the flow of current, flow of electricity. But if I made all three of those resistors the same value, they would have the same current going through all three of those resistors. But typically, the current through each component is going to be different. Now, to finish off this video here, let's talk about some real-world examples here on where parallel and series actually make a difference for us. Home wiring. Well, most outlets, or I should say not most, basically outlets in general, are connected. And if you just had to take a guess on it based off of what knowledge we know here, we know that if I take and put a plug into any outlet in my house, it's going to be 120 volts coming out of that. AC, of course, and RMS values, all that good stuff, but it's 120 volts coming out. Well, that means the voltage is the same, and then we can think of those outlets. Those outlets are kind of ways that I can connect electrical components. So an outlet, would be how I could like connect a resistor up, for instance. And actually, the old incandescent light bulbs, the easiest way to model an incandescent light bulb is with a resistor. So it's like, okay, well, we plug it in there and we get some, you know, uh, voltage that's dropping across there. But we know that the voltage is the same, so if I had to guess whether it's parallel or series, I would guess parallel because that's the only case of these two configurations that we talked about, and that is correct. Outlets are connected in parallel. Well, let's look at another one here, Christmas lights or holiday lights. I'll say cheap ones because some of the more expensive ones aren't wired like this. Cheap ones are wired in series. And how do I know that they're wired in series? Well, if I disconnect one light bulb in a string of holiday lights on the cheap ones, the whole string goes out. So if I disconnect a light bulb, for instance, take away that resistor, I now have an open circuit. Open circuit, no current flows through this. And so if no current flows through it, well, that means there's no current at all in the circuit. So R1 and R3 have no current going through it. And if you think of those as being light bulbs, if there's no current going through them, the light bulbs aren't lighting up. So the problem with that, of course, is if one burns out, finding the light bulb that is burned out in a cheap set of holiday light strings, it's easier just to buy a brand new one than to try and find it. Now, more expensive ones are actually wired not in series because one can burn out, and you can actually just see the light bulb that's burned out, replace it, and be fine. And those are actually wired in parallel. All right, so the next video here we're going to be discussing is actually some things we can do is about combining resistors and in series and parallel to get what we will call an equivalent resistance.